everyone, and thanks for watching Edupedia World Videos. We've completed the first 5 units which are an overview of mechanics, and in this video I'm going to introduce some advanced concepts and examples which I left out previously. These examples and concepts will not generally be used in your grade examinations, but might be of interest to you if you're giving some harder entrance examinations or if you just want to learn something new. The first thing I want to touch is, I derived many equations in rotational mechanics such as torque is equal to I alpha or torque is equal to dl by dt. But I gave these derivations without using vectors, assuming that everything is happening in a plane. I'll give the derivation, proper rigorous derivation of one of these right now, and you can attempt the others to see how it's done. Right, so let's take the second one. What is L net? The angular momentum. That is, if we take a collection of discrete particles, it is summation Ri cross Pi, right? Because L is R cross P for any single particle. We add each individual angular momentum and we'll get the total angular momentum, right? If it's a continuous system instead of a discrete, the summation is replaced by integral, and that's easy enough, right? So this means dl by dt for any system is equal to, we can use the product rule and say dri by dt cross pi plus ri cross dpi by dt, right? So that gives me summation I vi dri by dt will be vi cross mvi, which is pi, plus Ri cross dpi by dt will be fi external, right? Now the first term will be 0 for each individual particle because m is a scalar. Vi cross vi is 0, right? Because vi and vi have an angle 0 between them, so sine 0 will be 0. So all I'm left with is summation I Ri cross fi external. But what is that? That is tau I external, right? Because torque is R cross F, the moment of the force. That is equal to net tau external. The sum of each individual external torque is the net external torque, which is equal to dl by dt. So now I've proved this rigorously without any shortcuts, properly using vectors. You can try the others like torque is equal to I alpha using these similar results as well. The next important topic is, we've seen linear and rotational motion up till now, but now we'll see a combination of them. So linear motion would be a random system of particles in which every particle moves with the same speed in the same direction, right? So we can assume this whole thing to be a single particle moving along the same speed in the same direction, right? This would be linear motion. Rotational motion would be the same object moving about a point. It sometimes is the center of mass, sometimes it's not, sometimes it might even be outside the body, but every particle is moving about this object with an angular speed omega or an angular acceleration alpha. So this is translational motion, or we call it pure translational motion, and this is pure rotational motion. But generally motion is a combination of the two. For example, if you take a book and you throw it to a friend, the book will not generally be oriented in the same position always, right? Sometimes it will be facing up, sometimes it will be facing towards the right. So every particle will not have the same speed and the same direction. So that sort of motion in which you have a system which is also initially it's like this, then initially it's like this, and then, I apologize for the drawing, it's like this, but it's moving and rotating, right? So there's a theorem in advanced physics, I'll not prove it now, but it basically says that every motion which is a combination of rotation and translation can be decomposed into the linear motion of the center of mass plus a rotation about the center of mass. So for such a random motion, we can decompose it into a linear motion of the center of mass plus rotation in the center of mass frame. If we are sitting at the center of mass, we do not see the linear motion of the center of mass, we'll only see the rotational motion about the center of mass, right? And this is how we can solve many problems. So let's look at the first important quantity, angular momentum, right? So net angular momentum will do the same sort of analysis we just did right now, summation Ri cross Pi. That can be written as summation Ri. I'm just going to drop the i's right now, but you can assume they're there. Just for the sake of simplicity, I'm going to drop them. Cross, actually I'm sorry, dropping Ri might make a mess because we'll need it later on with center of mass. So summation Mi Vi, right? This is the net angular momentum. What I'm going to do is I'm going to decompose both Ri and Vi into position and velocity of the center of mass and with respect to the center of mass. So I'm going to write Ri as R, which is of the center of mass, plus Ri with respect to center of mass. This is R of the center of mass, right? Similarly, I'm going to write Vi as V of the center of mass plus Vi with respect to center of mass. This is basically the definition of relative velocity, right? V of I with respect to center of mass is V of I minus V of center of mass. V of A with respect to B is V of A minus V of B, right? So substituting these two in this, I'll get L. Now this is for a body which is both rotating and translating, not pure rotation, not pure translation, but a combination of the two, right? So I'll get summation I. So this cross this, right? I'm just going to write Mi outside, and then we'll get four terms, right? One will be RCM cross VCM. The second will be RICM cross VCM. The third will be RCM cross VI with respect to CM, plus the fourth will be Ri with respect to Cm cross Vi with respect to Cm. Right, 1, 2, 3, 4. We get four terms. Let's look at these four terms in a little bit detail. The first term, RCM and VCM are the same for every particle, right? Because they are the properties of the center of mass. So they can come out as common, and summation Mi will just give me the total mass. So the first term will be M times RCM cross VCM. We see that this is the angular momentum of the linear motion, right? I am into R cross V, that is R cross P. That is the linear momentum of the center of mass, i.e. we assume that the whole body is concentrated into a particle at the center of mass, and in that case the angular momentum will be M into RCM cross VCM. Plus, now let's look at the last term first, right? The last term will be RICM cross VICM. So it will be summation I Mi RICM cross, now VICM I can write it as omega times RICM, right? So RICM omega, right? Because that is V is equal to omega. And again we see the same property that omega is constant for all of them, right? So omega can be taken out. We get summation Mi Ri square. We get omega times summation Mi Ri square, which is just the moment of inertia, right? So we get I omega, right? Where I is the moment of inertia about the center of mass, and omega is the angular velocity about the center of mass, right? Plus we get two more terms. So let's look at those terms in a little bit detail, right? The first term is Mi Ri with respect to Cm VCM. VCM will come out as common in this, right? If VCM comes out as common, we get summation Mi Ri with respect to Cm, right? Now let's say we have a body and we take summation Mi Ri with respect to an origin. That will give me M times RCM, right? That is the definition of the center of mass. So that will give me a point like this, probably the center of mass. If I take the center of mass to be the origin, that means if I am taking all positions with respect to the center of mass, the position of the center of mass is 0 at the origin, right? So mi/ri with respect to center of mass will be 0. mi/ri summation will be position of the center of mass, but if we are taking everything with respect to the center of mass, the center of mass is at the origin, so this will turn out to be 0 in this term. So this is 0. Similarly, in this term, RCM will come out to be common, and we get summation mi vi with respect to Cm, which is again 0 by the same argument. Summation mi vi will be mass times the velocity of the center of mass. But the velocity of the center of mass in the center of mass frame is always 0, right? So these two terms cancel out to be 0. So this is what we get. And we see that these two terms would not have been 0 if we took it about any other point other than the center of mass. So we can take the angular momentum of any complicated motion of a body as the angular momentum of the center of mass plus the angular momentum about the center of mass, which is the rotational angular momentum assuming that the center of mass is at rest and everything is moving about the center of mass, right? So this makes results quite easy, and we'll use them in a couple of problems later on. But first we'll look at another important quantity, kinetic energy, and I'll do the same thing. That is summation half mi vi squared, which I can write it as summation half mi vcm plus vi with respect to cm whole squared, right? That becomes summation half mi vcm squared. Now we don't need the vectors because it's a scalar now, plus vi with respect to cm squared plus 2 vcm dot vi with respect to cm, right? Now the first term, summation half mi vcm square, is half capital M vcm square because vcm will come out to be constant. The second term we'll have summation half mi, and again vi with respect to cm, I'll write it as ri with respect to cm omega, right? And we'll square both of them. Omega square will come out to be constant. Summation mi ri with respect to cm whole square will be the moment of inertia about the center of mass, right? So I get half I omega squared, where I is the moment of inertia about the center of mass, omega is the angular velocity about the center of mass, plus, and this term will be 0 again by similar arguments because vcm will come out to be constant. Summation mi vi with respect to cm will be the momentum of the center of mass, but since we're taking it in the frame of the center of mass, it will be 0, right? So this is the kinetic energy. Again, we can see that it can be decomposed as the kinetic energy of the center of mass plus the kinetic energy about the center of mass, right? So we see that these complicated motions can be resolved into simple motions. Just like we resolved projectile motion into two linear motions in one direction each, we can resolve rotational plus translational motion into simply rotational motion, right? Let's look at a standard example which will use all of these concepts we learned up till now. This is probably as difficult a question as you're going to get in rotational mechanics, and so I'm going to use everything that I have in this question, right? The question is this. And again, I'll just write the equations. The emphasis should not be on solving the equations. It should be on understanding how the equations are written. So everything is happening on a plane. Whatever you're seeing, this is kept on the table, a smooth table, and the table is in the plane of the monitor, right? So we have a rod of mass m and of length L. This is the center of the rod. We have an object of small mass m moving with the speed v, and eventually it will strike this point, right? And this is L by 4, right? This hole is L by 2, this is half of that, L by 4, right? So we have a rod kept stationary, not hinged or anything, it is just simply kept stationary, right? And we have another object which hits it, and we are given that the collision is elastic. We have to find what happens finally. That means we have to find either the final speed of this or the final angular speed of this or whatever we want, right? We'll try to calculate everything. First of all, what will happen is these two will collide, so we'll have to use concepts of collision. Secondly, this object, this rod, let's say if it were hinged at the center. If it were hinged at the center, then it would simply start moving about the center. And it would be quite easy because we could be able to write the angular momentum as I omega and the kinetic energy as half I omega square. But in this case, it's not hinged. So in the second case, in a few seconds later, a few seconds later, it might be something like this. A few seconds further later, it might be something like this. That is not on, and you can visualize this, right? This particle, this rod will move a little bit towards the right because of the impact of the collision, but since the impact is not at the center, it will also start rotating a little bit, right? And a little while later, it might be something like this. So we see that yes, the center of mass is moving, it is moving towards the right, but not only is the center of mass moving, there is also a rotational motion about the center of mass. Again, we specifically take the center of mass because we derived in the previous results that when we decompose it about the center of mass, it becomes easier because the cross terms cancel, right? So let's assume the final result. The final result, let's assume, actually just for the sake of simplicity, I'm going to take this to be capital V so that our unknowns can be small letters, right? So it is initially moving with a velocity capital. Let's say finally this object is moving. It could either be moving forwards or backwards. We'll have to calculate and see what it is. Let's assume for now it moves forwards with a slightly slower velocity. So it moves with a velocity v1 after the collision. After the collision, let's assume the rod has a center moving with a velocity v2 and the rod has an angular velocity about the center equal to omega. Right? So let's start writing the equations. First of all, since there is no we are taking the system to be this rod plus this small particle, right? I'll also remove these for now. This was just to illustrate how we get it, right? How the motion will actually be. So I'll just write the equation in this place. I hope you've at least understood how it will be a combination of rotation and translation, right? That is important. So the first equation, I can write it as conservation of momentum, and that will give me the initial momentum is mv. Right, the initial momentum, I'm talking about linear momentum right now. Initial linear momentum of this object, I'm sorry about that. The linear momentum of this object is mv initially, and this is 0, right? So mv. What is the final linear momentum? Final linear momentum of this object is mv1. I would take minus mv1 if I took v1 to be towards the left, but I've assumed it to be towards the right. Plus, what is the linear momentum of this rod? Now this rod has a complicated motion, but we derived a result in center of mass even before we started rotational motion that the linear momentum is always equal to the mass times the velocity of the center of mass. Right, that had nothing to do with rotational motion. So we can write it as capital M V2. So this is our first equation. Right. The second equation, we'll have to use the fact that it is an elastic collision. Right. So elastic collision means that energy will be conserved. Right, conservation of energy implies the initial energy is half m capital V square. The final energy will be half small m v1 squared, that is the kinetic energy of this particle, plus the kinetic energy of this rod. And now you see the importance of using center of mass, because now instead of calculating the individual kinetic energy and adding that up, we can just calculate the kinetic energy of the center of mass and about the center of mass, and we just proved a few minutes ago that that will be equal to the net kinetic energy, right? So the kinetic energy of the center of mass will be half capital M v2 squared plus the kinetic energy about the center of mass will be half I omega squared, right? So half into I we calculated about the center, that is ml square by 12, right? If you haven't calculated yet, you can try to do it, it's easy enough. So ml squared by 12 omega squared, right? We have two equations, but we have three unknowns. We need a third equation. The third equation we can get by conservation of angular momentum. Now, about which point do we conserve angular momentum? The truth is that if the torque, external torque about a point is 0, then angular momentum will be conserved about that point. So we can conserve angular momentum about this point, or about this point, or this point, or this point, or this point, any point. Right? Now you might start to think we might end up with some inconsistencies. We could have 3 unknowns and 50 different equations. But I'm going to conserve the angular momentum about this point, and I'd like you to try to conserve the angular momentum about this point, or a point 100 meters above this, and you can see, you will be able to see that the actual extra lengths will end up cancelling, right? Just like if we take the difference in heights between 2 points, we can take default 0 to be anything, the difference is what matters, right? So I want you to verify at home that you can conserve angular momentum about any point, and it will ultimately give me the exact same equation, right? Not different equations, one equation, no matter how many times and how many different points you use. So I'll just conserve angular momentum at this point. The initial angular momentum of the rod is 0 because the velocity is 0 of the center of mass and omega is 0. The final angular momentum, the initial angular momentum of this particle is small m capital V L by 4, right? R cross mv, right? So mv will be this, R will be this, right? And the angular momentum has a sense of this, that is, it has a sense facing towards you, right? mv into L by 2. Final angular momentum will be m v1 L by 2, that is the angular momentum of this, plus the angular momentum of this will first of all be the angular momentum of the center of mass, and then the angular momentum with respect to the center of mass. The angular momentum of the center of mass in this particular case is 0 because I have chosen the center of mass as the point, so R will be 0. If I wanted to conserve angular momentum at this point, then we would also have an angular momentum of the center of mass. Remember, the angular momentum of the center of mass will simply be an angular momentum of a particle of mass m moving with the speed v2. In this case it's 0 because we are conserving about this point, and that is actually why I chose this point. Right, that's the analog of what point do we take torque is equal to I alpha about? The point through which we get the minimum number of terms. And the angular momentum about the center of mass will be I omega, that is ml square by 12 omega. We see that we got 3 equations and we have 3 unknowns. You can solve them, and in some cases, depending on the masses, you might get v1 to be towards the right, you might also get v1 to be towards the left if capital M is much greater than small m, right? So this is probably as difficult a question as you can get. You can add other concepts to this question as well, but you can add a spring if you want, for example, in this question, or you can add another collision. But the important thing in solving questions like these is you need to draw a free body diagram and you need to know how the equations came about. Solving these 3 equations is the trivial aspect, right? It's important to know where these equations come from. So I'll write it. This equation comes from the conservation of linear momentum. This equation comes from the conservation of kinetic energy, and this equation comes from the conservation of angular momentum, right? There's one final concept that I left out purposely which I want to teach you, and that is variable mass systems. It is one of the trickiest concepts and generally not used in basic physics examinations, but sometimes it is used, and it deals with this. We saw that Newton's second law actually in its purest form reads F is equal to dp by dt, rate of change of momentum, and we wrote it as equal to d of mv by dt, and we took m to be out because m was a constant and it was dv by dt, and it eventually became equal to ma, right? But in that case we made an assumption that m is constant, the mass is constant. There are many situations in which the mass is not always constant. For example, if you have a road on which you have a vehicle carrying a lot of water and there is a hole at the bottom, so water will keep leaking out, and as the vehicle moves forward, the mass of the vehicle will keep on decreasing. So in such cases, F is equal to ma is not strictly valid. We get another term, that is V times dm by dt, right? And that is not always equal to ma. So up till now we've only seen questions in which the system has a constant mass throughout, right? The previous question we took the rod plus the particle to be the system, and the net mass was small m plus capital M throughout. That did not change. What do we do in cases where mass does change? The best way to do it is not to go in terms of v dm by dt, but use simple momentum conservation, because momentum conservation is still valid. And the standard example in which this is used is rocket propulsion, because this is the basis on which rockets move. So the question I'm given is this. Let's assume I have a rocket that is moving forward, and it is moving forward by ejecting fuel, right? It ejects fuel at a rate r kilogram per second, right? So every few seconds it ejects a certain number of kilograms, and so the mass of the rocket keeps on decreasing, right? And the fuel is ejected at a speed u, and this is the crucial part, at a speed u with respect to the rocket. So speed u is not with respect to an inertial frame or with respect to space, it is with respect to the rocket, right? That's generally given because it's easiest to measure the speed of fuel exiting a rocket, relative to the rocket, because generally the people who will be measuring the speed of the fuel ejecting will be stationary on sitting on the rocket, right? It's harder to measure how much fuel is ejected at what speed if you're sitting on the ground. So U is generally given with respect to the rocket, right? The initial mass of this rocket was m naught, which continues to decrease as time increases, and because of conservation of momentum, this whole system still has the same mass, right? If we consider only the rocket to be the system, mass is decreasing, but the whole rocket plus fuel has the same mass and momentum will be conserved. So if fuel is ejected backwards, that will propel the rocket forward. That is the principle by which rockets move through empty space, right? Rockets do not move through air. They cannot use the principles of fluid mechanics like aeroplanes use. They have to move through empty space. So this is the only concept that they're able to use. Our question is, if it starts from a certain speed or if it starts from rest, what is the speed after a certain time, right? So the way you solve these or other questions involving variable mass systems is this: you take an instant of time, slightly after that, and you conserve momentum between the two. So let's say at a time the rocket has a mass m and the rocket has a speed v, right? After a little bit more time, the rocket has a mass m minus delta m and the rocket has a speed v plus delta v. Right, as time goes on, the mass of the rocket keeps decreasing, and the mass of the speed of the rocket keeps increasing. Right, so we'll conserve the momentum between these two. Initial momentum is mv. Right, final momentum. Initially, the momentum is mv because we take the rocket plus the fuel that's not yet ejected as a system. That will be equal to, in the next instant, m minus delta m time v plus delta v plus, actually let me just draw the figure, it will be slightly clearer. Right now we have a rocket which has a mass m moving at a speed v. The next instant the rocket has a mass m minus delta m. It is moving at a speed v plus delta v. I am technically supposed to use dv and dm because I am talking about an infinitesimal time interval, but I am going to use delta for the sake of clarity, right? Eventually I'll get to d. And there will be fuel. The mass of the fuel will be delta m and the speed of the fuel will be u, right? But it will not be u actually. U is with respect to the rocket, right? So we'll have to find the speed with respect to the ground as well, or empty space, right? So actually this will not be plus, this will be minus because it's in the opposite direction. Delta m times the speed of this, right? So what I need now is the speed of the fuel with respect to the ground. The speed of the fuel with respect to the ground will be the speed of the fuel with respect to the rocket plus the speed of the rocket with respect to the ground. Sorry, instead of speed I should say velocity. So velocity of the rocket, of the fuel with respect to the rocket, is u, right? And the velocity of the rocket with respect to the ground is v towards the right. So it will give me u minus v. U minus v. Right? And this is the important part, tricky part. So I'll repeat it again. We wanted the velocity of the fuel with respect to the ground. That will be the velocity of the fuel with respect to the rocket, u, plus velocity of the rocket with respect to the ground. That is minus v because we've already put a minus here and we are calculating the velocity in this direction. Right? So now let's try to analyze this. I'm going to remove these diagrams. Yeah, so we'll get capital MV is equal to capital MV minus delta M times V plus capital M times delta V. Now what I'm going to do here is I'm going to ignore the delta M delta V terms because actually we are talking about very small instants and delta should actually be a D, and if we take two very small things, they'll be negligible compared to these. Delta M might be 0.001% of M and delta V might be 0.001% of V, even smaller than that actually. So if we multiply them, we'll get a very small quantity and we'll ignore that, right? So minus delta MU plus delta MV. MV directly cancel. We get delta MV and delta MV cancel. So we get m times delta v is equal to delta m times u, right? And what this gives me is, I'll write d instead of delta. So m dv is equal to dm u. So I get dm by m is equal to dv by u. Right. Now I can integrate these two. Right. So that gives me ln of, if this probably goes from m naught to m, and this goes from 0 to v, right? U is a constant. So ln of m by m naught is equal to v by u, or I get v is equal to u ln m by m naught, right? So this is the final result, which tells us the speed of the rocket in terms of the speed of the fuel ejected, the initial mass, and the mass at any time t. This is how you solve problems involving variable mass. You take two instants of time and you just conserve momentum between the two, right? This completes our unit of mechanics, and I hope everything has been clear to you. Thank you.